Now, this is a very important relation. So, if I ask you what minus nk sum over I rho epsilon I, where rho is the probability which we have defined before, rho ln rho. So, what does this expression correlate to? How this expression or what this expression relate to what thermodynamic quantity? And as I had defined before, rho again to remind you that this capital N and small n, they are the same thing, and they are the total number of particles. Rho EI is the probability which I had defined before, is n by ni by n, and therefore it is minus e to the power minus beta epsilon I by q. So, probability is nothing but ni by n, number of particles in I state divided by total number of particles, and from Boltzmann distribution law, ni by n is nothing but e to the power minus beta epsilon I divided by the partition function. So, that is the probability. So, now the question is what this expression, what thermodynamic quantity this particular expression relates to. Let us find out. So, minus nk, we put it up, we put up rho EI as it is, and now we are replacing this rho EI with this expression, which is e to the power minus beta epsilon I divided by q. If we simplify, we get nk ln q, we can so this ln q, if we bring out here, so that minus and this minus becomes plus nk ln q sum over rho epsilon I, and that is kind of the second term we written first, and the other term here. So, ln e to the power minus beta epsilon I is nothing but beta epsilon I. So, that minus beta and nk we write as b nk sum over epsilon I rho epsilon I. Again, so here, so minus nk sum over rho ln e to the minus beta epsilon I by q. So, I am just writing this term first. So, ln 1 by q comes out with a negative sign, and that negative with this negative becomes a positive nk ln q, and we had this term rho EI plus this term ln e to the power minus beta epsilon I is nothing but beta epsilon I. So, that beta comes out of the sum beta nk, and inside the sum we have epsilon, this epsilon I with rho epsilon I. Now, sum over rho epsilon I is nothing but 1, because total probability is 1. So, therefore, we get nk ln q plus nk beta is 1 by kt sum over epsilon I, again rho EI, as you know, it is nothing but ni by n, as I said, ni by. So, now I defined total number of particles as n. So, again nk ln q plus this k goes off. So you have n by you have n by t, and this n comes out 1 by n, and sum over ni epsilon I is nothing but the total energy. So you get nk you get nk ln q plus this n goes, and this is total energy. So you get E by T. And so if you remember this expression, nk ln q plus E by T is nothing but the entropy. So therefore we write S is equal to minus nk sum over rho ln rho I. So now you look at here. So this is a probability. So probability is always less than 1. Therefore, this quantity, the whole quantity will be positive, and that is the second law of thermodynamics. Since probability is always less than 1, so total quantity in the right hand side will become positive, and that implies that entropy of the system always increase, and that is nothing but the second law of thermodynamics. Okay, so we got entropy is equal to minus nk sum over rho I ln rho I. Now rho I is the probability which is always less than 1, and if rho I is always less than 1, what will be your entropy? Yes, entropy will be positive, and that is the second law of thermodynamics. That is the second law of thermodynamics, that entropy of the system or randomness of the system increases. So again, as you see that the probability is again a microscopic quantity, can also explain the thermodynamic laws, the basic thermodynamic laws.